Yeah, thanks, and thanks for the organizers for having me here. It's a pleasure, of course. Yeah, so today I'm going to give you more of a computer science perspective on some of these questions about dynamics and entanglement in non-equilibrium systems. I think as Matthew mentioned, there are these nice connections between quantum information theory and many-body physics now, so hopefully some of this is informative. Okay, so yeah, this is a collaboration with people listed here. In particular, Bill Pfefferman has sort of been teaching us about complexity theory aspects of these problems. And we have a preprint which was presented at QIP. One thing I want to highlight is there's a related work that came out around the same time which kind of explores different aspects of this problem. I think when you put these two works together, you get really a nice picture for what I'll discuss today. And then some work I won't talk about, but which is also very interesting and connected to these measurement-induced entanglement transitions, is trying to use that kind of physics to develop classical simulation algorithms. Okay, so what we're going to talk about today is noisy circuits without error correction. So this is what we commonly call NISC in the present days. And what this NISC era is about is this fundamental trade-off between the sort of system size and the noise that you can tolerate. And so in general, you can sort of achieve large systems, but then the noise rates tend to go up, so it's challenging to do both. And what we want to do in this work is really quantify this trade-off between noise and system size and sort of extract what we mean by the quantum signal. And we'll use these ideas of complexity theory to kind of motivate the observables we look at. Okay, so these kinds of considerations are important for algorithms because they teach us which algorithms are going to work in practice on current hardware. And this setting we're going to study today is probably will be a theme in different talks in this meeting. We'll be looking at these random circuit systems, and as is well known, these have a number of applications in quantum information. So in particular, there's a proposal by Google that you can have quantum computational advantage from sampling from random circuits. That's without noise. And then they're also, they've been used historically for many years just in benchmarking quantum systems. They also show up in sort of studying typical behavior of near-term algorithms. In recent years, they've been of great interest for studying physics of many-body systems. And there's also this notion that if you just run a random circuit, you get exponential growth of state complexity, which is an interesting aspect. Okay, so now let me move on to the model we'll consider. So this is we're going to study one of these brickwork circuits called parallel circuit architecture. So you should have in mind there's two kind of key parameters for us. There's the n, which is the number of qubits, and there's a depth d, which is the sort of number of layers of the brickwork. And then the size of the circuit is the product of those two. So that's S is the product. And the output is we're going to measure each qubit in the computational basis, and we're going to get a bit string at the output. And and the input will be a computational zero state. So a very conventional setting. Okay, so what's going to go inside of these little blocks are these Haar random 2-qubit gates. And one thing we'll focus on in today's talk is looking at a noise model, which are called stochastic polynoise. And so they're quantum channels which can be written sort of in this form. At first glance, they look somewhat artificial, but they sort of capture the basic effects of noise and increasing entropy in quantum systems. And they play an important role in quantum error correction. Okay, so the noise strength, which is this parameter gamma, is just going to be the number of, the probability of getting a non-identity poly on a given site. And so the intuition is that this type of polynoise that generally adds entropy to the system but never decreases entropy. So in general, this type of system will just flow to a maximally mixed state. But what we're interested in today's talk is actually understanding that that question more precisely. So how how quickly and how does it approach the maximally mixed state or the uniform distribution on the output. And the two quantities we'll study are something, these are measures in, say, probability theory. So this would be the total variation distance to uniform. So it's just a metric on the probability distribution. So you have the noisy random circuit, and you look at its distance to the uniform distribution. And we'll also consider something called anticoncentration, which I'll get to later. Okay, so actually, as you can imagine, this type of setting has been studied for a number of years, actually going back to really foundational work in the 90s on noisy systems. And previous work has put upper bounds on this distance to the uniform distribution. So there's this original work by Aronoff, where what she studied was a model where after each gate you had depolarizing noise. And what they were able to show is that the total variation distance decays exponentially in the depth. So the total variation distance is growing down exponentially. And for random circuits, so this is specific to depolarizing noise. So for random circuits and more general noise models, there've also been improvements showing that you get similar exponential conversions. But what kind of motivated this work was that, or part of what motivated this work is that there was this observation from the Google group that this decay might be a very weak upper bound. In particular, they saw evidence that random circuits converge to uniform and exponential in the size of the circuit. So not just the depth, but also the number of qubits. And this is very bad news for noisy circuits. So we wanted to understand that better. And so one of our main results is about lower bounds on this total variation distance. And so I'll present that. Okay, so what we were able to show using relatively simple arguments is that for arbitrary local polynoise, there's a lower bound in the total variation distance, which is again linear in the depth. So not in the size of the circuit, but in the depth of the circuit. So what this implies is that previously there were these upper bounds known on the convergence to uniform, and this is showing that those are really tight. Those are really capturing the behavior of noisy circuits. So one application of this is it disproves this conjecture from Google that the scaling was with the size of the system. And one interesting feature is that it turns out what they were observing is like an intermediate regime. So if your noise rate goes to 0 in the thermodynamic limit, then you do actually recover this kind of behavior. And the intuition is that a local error will get scrambled by the random unitary circuit, and it sort of acts like a global depolarizing channel. So what our case considers is this limit of a constant noise rate, which is a more natural limit to consider. Okay, so let me give you some intuition for how we arrive at this lower bound. So one thing that's kind of nice is that just using basic information theory, you can convince yourself that you actually don't have to study the whole output distribution. You can just study local density matrices. So we actually studied, how quickly does even just a local reduced density matrix on 1 qubit converge to the uniform, and that's sufficient to achieve the lower bound. And what we show is that these local density matrices are far away from the identity matrix, and the method we use is actually a trick where you replace Haar circuits by Clifford circuits and then use second moment properties, the two design property of the Clifford group. And yeah, so that explains the behavior. The physical intuition is that at this kind of low depth, the density matrix can't really know how many qubits there are in the system, so we sort of intuitively expect this kind of behavior. Right, okay, so I also want to discuss some improvements we had on upper bounds for this problem. And this was actually motivated by thinking about these measurement-induced phase transitions, which are sort of very special noise model in some sense, because they have this additional feature that the locations of the measurements is actually heralded. It's sort of known to the user. So even if you forget the measurement outcome, you still know the location of the measurement, and you might think that that's a weaker setting that would allow you to circumvent these upper bounds, and maybe there's still a phase transition in that limit. So what we were able to show is that's not the case. So if you throw out the measurement outcomes, you converge again exponentially with depth, and right. So this rules out this phase transition with unknown measurement outcomes. And the method is, again, relying on these statistical mechanics mappings that Matthew alluded to. And so the idea is, it turns out, is very simple. So we use second moment properties to write down a statistical mechanic model for this system. And then it turns out that you can maintain this upper bound, and this is why there's no phase transition, by replacing all of the two-site gates by single-site gates. So essentially, the scrambling is not helping you in this noisy setting. And so when you have a circuit with just single-site gates plus noise, you converge to the uniform quickly. So that's the intuition. Okay, so now I want to tell you about some of the implications of our work for quantum advantage from random circuit sampling. So it's, as I alluded to, it's believed that so sampling from noiseless random circuits it has this quantum advantage feature, assuming some conjectures in complexity theory. And so the sampling problem. So what we want to do in this setting is reduce the sampling problem to a computing problem. So what we're interested in is approximating the output probability of the all zero bit string. And what we want, to show sampling hardness, it's sufficient to show that computing this to this precision of 2 to the minus n is hard. And that just comes from the Hilbert space dimension. And so we have this axis of imprecision here. And what we want to get to in this setting is this 2 to the minus n. But what's been achieved is actually hardness to precision, which scales with the size of the circuit. So S, which is n times d. So it's much higher precision than what's needed for sampling. And I guess what's interesting is that the methods that are used here, they don't rely on the absence of noise. So actually, this hardness applies for noisy circuits. But we also know that if you just sample, there's sort of obviously trivial algorithms for sampling from a very noisy circuit. So there is this tension between precision and for computing and precision for sampling. Okay, so one of the questions was whether this hardness for computing to this precision was sort of optimal for the current proof methods. And so the interesting view on this was to look at noisy circuits. And so what you can show is that because as we showed this convergence to uniform, it scales exponentially, then actually there's a trivial algorithm for computing, which is to just guess 1 over 2 to the n. And that gets you to the required precision. It's obviously very simple, but that turns out to achieve this kind of precision. And so if this total variation distance scaled like the Google conjecture, then the previous proofs for the hardness would have been optimal, and there would be no way to sort of break this barrier. But based on our results, there seems to be room to improve the proofs for hardness of sampling. Okay, so how am I doing on time? Okay, yeah. So right. So now I want to tell you about anticoncentration. So this is a property which essentially measures how spread out a distribution is. The reason it's important for this sampling is that if you have a Haar random circuit, you want it to be close to the uniform distribution in some sense, because you don't want it to put too much weight on any single bit string. And so this sort of measures how much weights are on particular bit strings. So when you have an anti-concentrated distribution, the this is what it would look like. It's roughly uniform. However, if you have something which is not anti-concentrated, then the mass sort of concentrates on a few outcomes. And so, yeah, that's kind of the picture you should have in mind. So yeah, so there's a formal definition in terms of this concentration of the probability, which is shown here. I guess what's interesting is that this anti-concentration, it's sort of not necessary for hardness. So one example related to this to connect to the measurement transition is you can, the output distributions, if you sampled from, let's say, the volume law phase, the output distribution would not be anti-concentrated. It would have weight on particular bit strings. But there could still be hardness for that sampling problem. It's just much harder to prove in that case because often you need this anti-concentration property. Okay, so some of our results also improve the understanding of anti-concentration in random circuits, noisy and noiseless circuits. And the reason this is interesting from a physics perspective is you can think of anti-concentration as probing the thermalization time of a random circuit. And one thing you can show is that anti-concentration follows from a two design property, but that's actually not necessary. And in particular, for two designs, you typically need like linear depth, so very high depth linear and n for a one-dimensional system. But it was proven that actually logarithmic depth is sufficient. And so it's a much weaker notion of thermalization than like a design property. And so we wanted to know if these could be improved further with our methods. And so we were able to show that if you take sublogarithmic depth, you actually get a severe lack of anti-concentration. So this log depth is really tight for anti-concentration. So that suggests that if you're looking for hardness of sampling, you should really be looking in this logarithmic depth region. And this arguments again apply for both noisy and noiseless circuits. Okay, so yeah, one application of this lack of anti-concentration result is to constant depth circuits. So there was a result that showed that even though we have this worst case hardness for for constant depth in 2 dimensions, there was a result from Knapp et al. Which showed that it's actually average case easy. They used a mapping to the measurement-induced phase transition to show that there was an easiness algorithm for very low depths, and that was based on matrix product states. Okay, so what we showed is because we showed there's no anti-concentration in this regime, there's actually a trivial algorithm which doesn't rely on matrix product states, which achieves the same result. So you can actually compute this quantity to needed precision just by outputting the trivial amplitude. And I guess the important observation though is that our algorithm, this algorithm is not a sampling algorithm. And so these kinds of methods are much more powerful because they give you a sampler for the distribution. Okay, so just to summarize, so I told you about this problem of how fast noise takes you to the uniform distribution in noisy circuits, and we found this tight scaling with depth, and then I presented these results on anti-concentration. And these results are interesting because of the implications they have on these wide range of problems. So it was an interesting study. Okay, so some of the outlook for this work is that as I mentioned in the talk, there's really a lot of room to improve the proof techniques for hardness right now. I mean, they're at this very almost unrealistic level of imprecision, and it'd be very nice to improve that to higher precision. Another aspect which is interesting to consider is that we were actually focused on the average, the sort of circuit average value the distance from uniform. But you can also ask about the typicality of delta, whether like a typical circuit is also, how close or far is it to uniform? And perhaps what we found is just a property of rare circuits. But yeah, so it's interesting to study the typicality. And we have evidence now that actually it is that what we showed is actually the typical behavior, so with high probability. So this is also relevant for these variational quantum circuits, where you have these barren plateaus that arise at high depth. So the general outlook of our work for algorithms is that this logarithmic depth is really the sweet spot for NISQ, at least in the limit of large system sizes. Right, and then another interesting aspect that we're exploring is that this idea that, that what's central to this hardness results is this idea of precision, that, computing things to very high precision often tends to be very hard from a complexity theory perspective. But as you reduce the precision, you can really make a lot of gains in algorithms. And so that has important implications for developing simulation techniques for like benchmarking quantum circuits and also maybe simulating fault-tolerant quantum computing circuits, with the idea being that perhaps we can simulate and optimize fault tolerance without without having a full sampler for the quantum circuit. So thanks for your attention.